Greetings and welcome back. So, in this vignette, what we're going to do is we're going to get started on a very important section of the course. And this one is really engendered by the modern world of computation. When I say computation, I mean it in the context of our capacity to do huge calculations, store huge amounts of data, and so on. And that's led to what I consider to be a natural extension of hundreds and hundreds of years of different ways of representing the world around us mathematically. You'll see what I mean by that. And of course, it will lead us into the world of machine learning and AI and trickery such as PCA and so on. So this will probably be on the order of 5 or 6 vignettes. So the idea is I'm going to start with an abstraction of what I mean by the word representation, and I'm going to be semantically imprecise because the word representation has lots of connotations for me, which I hope you'll find amusing. Then the next vignette, what we'll do is we'll talk about the way in which the notion of vector has been extended in light of our use of lists on computers and so on. And then we'll turn to the idea of what are the best variables or coordinates. That will lead us to things like dimensionality reduction, PCA, and so on. So how do we represent the world around us? That's really interesting. You know, if you think about it on this particular slide, there's a convention, there's a representation that we all have in terms of the language we use of the notion of red. And I feel very confident that my listeners can see that there are 2 lines here, which are the axes of my Cartesian coordinate system that are what we call red. But I'm also confident that we could wander around in the world outside and we could point with our fingers and say, you know, that's red, the stop sign over there, that's red, that car is red. And yet, you know, the actual wavelengths are slightly different. So we have this notion of a representation in terms of redness. So for my courses, for the things I'm talking about here, the answer is often mathematical when I talk about a representation. And here, I'm just trying to point out that we can come up with alternative representations of the geometry of New York City. And what's interesting about that is that though we have these different choices of coordinate systems that are equivalent in their answers, in other words, if I want to tell you how to get from Central Park South to Rockefeller University, I could describe it either in polar coordinates. It would be odd, but I could say, you know, go at angle 46 degrees or whatever it might be and travel a distance of such and such miles. But it's a lot more sensible in some sense to exploit the natural Cartesian coordinate system that describes the layout of Manhattan. So psychologically, they are definitely inequivalent, despite being, in terms of their answers, completely equivalent. We're really accustomed to viewing the Earth as a Mercator projection, but as I say, you know, it's a representation, and one of the reasons that I can point that out is that the area of the United States and Canada are roughly the same, and the area of Greenland is quite a bit smaller. And yet, when you look at this map, you know, our minds are somehow tormented by the fact that we've taken something that exists on a sphere and we've projected it. So it's a representation, and it's a representation that has mistakes in it. And that's something mathematicians have thought about deeply, going back to Euler and Gauss and others. But there's all sorts of different notions of representation, and here, you know, I choose one of my all-time favorites. We're visiting Newton in his study. The young Newton, between the ages of, say, 20 and 25, he was locked up in basically a plague and went home to Woolsthorpe from Cambridge. And while he was there, one of the things that he did was to think about the area under the function 1 over x. So maybe many people don't know this, but at the time of Newton, people already knew how to do what we would now call the integral of x to the power m over n, where m and n are integers, with one exception, which is x to the minus 1, which is shown in the upper left of this graph. And so Newton realized that he could represent the function log of 1 plus x as this series. And there's a way of writing the integral dx over x using his understanding of the series expansion of 1 over 1 plus x and 1 over 1 minus x. The details of this don't really matter, but the key point that I want to make here is that he can then do his integral dx over x term by term. That gave him a series. And then what he's showing us in this particular graph is the series itself, which you see right here. I've rewritten it in modern terms at the top. And then what he did is he said, let me imagine, as you see right here, he says, let me imagine x equals 0.1, so we're going to take the log of 1.1. And he works out all the terms in the series out to roughly 50 decimal places. Why do I bring this up? Because this notion of a Taylor series, in its most naive form, it really amounts to representing a function by a very low-order polynomial. And I show you that over on the right-hand side, where we see the representation of log of 1 plus x up to quadratic order. So to me, that's a vector. There's 3 entries in the vector, 0, 1, and minus 1/2. So it tells me the weights of x to the 0, x to the 1, and x to the 2 power. Similarly, for e to the x, I can represent that as a vector, 1, 1, 1/2, where those are the weights of x to the 0, x to the 1, and x to the 2. So you see above, y is 1 plus x squared over 2. And finally, for sine x, we represent that as well as a vector, 3-component vector, where there's only one term because our approximation is the straight line. So what was my point? My point was that mathematically, it's very convenient for us often to represent a function, some messy function, by some low-order polynomial. Another example of this is Fourier series. So we will come back to this in subsequent vignettes, but the point I want to make here is, Fourier was this quite brilliant, persistent physicist, mathematician. He really was both. He was primarily, in the early 1800s, interested in the theory of heat. He was disappointed, or at least he was unsatisfied with Newtonian mechanics as it pertained to the subjects of temperature and heat. And so his analytical theory of heat is essentially, in many ways, similar to Newton's Principia. It attempts to cover the entire waterfront of a whole new category of phenomenology, which in his case refers to heat. Now, in order to solve the heat equation, he found very general techniques based on what we would in modern terms call the Fourier series and the Fourier transform, or the Fourier integral. And all I really want to get across here is that on the left, I have a function that I want to represent. It's a messy function. It's a sawtooth. It's periodic. It goes from minus infinity to infinity. And what I'm showing you is that we can represent that function as a series, a sum over sine waves. And if we truncated that series after 5 terms or 10 terms or whatever, that means I would be representing the triangular wave by 5 or 10 numbers. Those numbers are what we call the Fourier coefficients. In this case, they are the parameters 2 times minus 1 to the n plus 1 over n pi. That is the nth component of the vector that represents the sawtooth wave in terms of sines. So, to me, the Fourier series is an amazing example of a representation of a function by a new way of seeing that same problem. So, the way that I think of it is that we start with a particular thing of interest, and then we find a way of reframing that thing in a new encoding. Same object, new encoding. This is one of my favorite examples. So here, I'm thinking about the symmetry of the triangle. So if I asked you to close your eyes, I rotated this triangle by 120 degrees and told you to open your eyes, you'd be none the wiser. In other words, it's a symmetry of the object. You wouldn't be able to tell that I'd done anything. The fancy words that we would use to describe that is that there's a group, there's a set of operations that I can perform on this object such that it is unchanged. And the simplest version of that is to represent it by this multiplication table. And I've got 3 operations that I can perform. I'm calling I the operation of doing nothing. I'm calling R 120 the operation of rotating by 120 degrees. I'm calling R240 the operation of rotating by 240 degrees. And what I want you to see is that there's a multiplication table, meaning that I can put these operations together in succession. So for example, R120 times R120, as you can see in the multiplication table, is R240. That makes sense. R120 times R240 gives me the identity, because if I do a 120 and a 240, that's a full 360 rotation, so I'm back where I started. Interestingly, I can represent this same symmetry group, the same set of operations, by the 2 by 2 matrices shown over here on the right. What I'm saying, and I offer it to you as an exercise, is that if you multiply those matrices together using the conventional rules of matrix multiplication, you will see that they represent the same set of symmetries as shown in the multiplication table. Even more intriguingly, and I leave it as an exercise to you to figure out why those are the matrices, you can work this out on your own by labeling the three vertices A, B, and C, and then thinking of the vertices as a vector, A, B, C, and then the matrix takes the current configuration ABC and turns it into a new configuration. For example, A goes to B, B goes to C, C goes to A is a 120 degree rotation. That 3 by 3 matrix set of matrices also represents the symmetry. So what I'm saying is there's this fascinating thing, which is I can represent the symmetry of the equilateral triangle or the square or a rectangle or whatever using this idea of operations that leave the object unchanged. This is a very huge, important subject in mathematics. It's used a lot in physics. For my purposes today, I'm using it really as a metaphor. I'm not thinking about it in the deep mathematical sense particularly, but I'm just noting and wanting you to appreciate how wild it is that I have these different matrix representations. A similar thing happens in the context of deformation of materials. If I take a piece of jello and I subject it to a uniform expansion, or I push on the top and I shear it, or I twist it, or whatever, all of those things can be represented by the so-called strain tensor. I'm not going to go into the details right now, but really what I'm saying is that if I want to go into a material and find out how it's been deformed, I'm saying that this set of 9 numbers locally tells me the disposition of the material elements inside of that material. So at each point in space inside of the material, there's a strain tensor. That strain tensor reports to me the extent to which that local piece of material has been deformed. We're also used to representing things by passing back and forth between discrete and continuous representations. If we were in a classroom right now, what I would do is I would take a water bottle and I would pour it on top of my head. And the reason I would do that is I would do it as a protest to the idea of water as molecules. I would say, look, this seems awfully continuous to me. It's done tongue-in-cheek, but it's extremely interesting that we have these two ways of holding in our minds the same object. And we've already seen that in the context of diffusion. Diffusion can be a series of coin flips where each player moves left or right at every coin flip. It's discrete. And if I average over many such players, I get a continuous distribution. On the other hand, I can just treat a concentration field C of x and t, and it's defined at every point in space, and that's an equally legitimate representation of this discrete collection of molecules. So here on the lower left, you see patterns of currents in the ocean, and we know that the ocean's made up of H2O molecules, but I can suppress that and represent it by this continuous field of density and velocity. On the lower right, that's Baja California, and you see vortices being shed off of an island due to a southerly flow of wind, and the clouds basically form these patterns, and so the atmosphere is also a collection of molecules, O2 and N2, but once again, I can treat it as two fields, density and velocity. Something that I will likely come back to again and again is the idea of graphs as being one of the best kinds of mathematics for modern science. So I think that graph theory is going to turn out to be one of the hidden secrets of the nature of the living world. And here I just want to point out that, very different, distinct problems can be mapped onto problems where we represent whatever it is that's going on as a graph. So the one at the top is the very famous Bridges of Königsberg problem of Euler, where the question was whether or not he could make a Sunday afternoon walk, passing over only each of the bridges but once. The lower left is the 1800s. This is the work of Kirchhoff, who thought of circuits as graphs and was able to find out the current, the voltage, and so on within a circuit on the basis of these graphical representations. And then the lower right is something that I have specifically learned from Jeremy Gunnar-Wardena, and that is to represent the various states, for example, of a genetic network or a signaling pathway as nodes on a graph. So why I'm saying this is advertising or tourism. Hey, look, pull up your binoculars. There's a wildebeest over there. Just saying, pull up your binoculars. Hold this in your mind, that the graph is a representation of networks in a very powerful mathematical way in which we can dissolve the specifics of what led to the graph and just focus on the mathematics of the graph itself. In the modern world meaning a world full of computers, this is in many ways one of the most important representation slides that I can offer you. And so on the top, what I'm showing you is the use of finite element shape functions. So just as a little plug, we have hundreds of years of people being extremely clever about solving differential equations in which the system had a very high degree of symmetry. That led to specific functions that represented any function in that interval. Fourier series I've already talked about. That tells us how to represent periodic functions. Spherical harmonics tell us how to represent functions on spheres. Bessel functions tell us how to represent functions on cylinders, and so on. But the way you might say this is that and mathematical physics has this history of terrible geometries, but incredibly clever basis functions. So spheres, cubes, cylinders, those are good. I mean, they're fun, they're interesting, but they're not very generic for, the world around us, in which most of the objects are not that clean. If I take a car, I'm not going to represent that in terms of those kinds of functions. So with the advent of computers, we learned a different idea, which is let's use terrible shape functions but do great geometries. So when I say shape functions, what I mean is literally to use linear interpolation, for example. So shown in the upper left, I've actually solved the Schrödinger equation for the particle in a box by hand using finite elements, where you essentially say that the wave function is represented by a straight line between nodes. So really the only degrees of freedom are the amplitudes on each node. That's it. And everything in between is done by linear interpolation. In the upper right, I show you these tent shape functions. So for example, if I wanted to represent the deformation of a two-dimensional material, I could calculate the displacement at every point in terms of those shape functions. So that's a representation. On the bottom, I'm hinting at the modern world of machine learning, or using composition of functions, the way that Gilbert Strang likes to put it, in order to construct functions. And here's my simple statement. Using these kinds of functions, I can make step functions and I can make delta functions. If I can construct delta functions, then I can essentially create any arbitrary function within limits. And so, by using these extremely simplified things, which are basically a thresholded line, so, the blue ReLU of x minus x naught tells me that if x is less than x naught, it's 0. And if x is greater than x naught, then I just take x minus x naught, and that's the value of the ReLU at that point. If I take the difference of two ReLUs, meaning take the blue one minus the red one, I get a step function. And if I have a step function and I take a difference of two step functions, I can get basically a skyscraper. And I can construct functions out of skyscrapers. Just as an aside, in terms of least squares and regression, it's another kind of representation. So just as a little story, in 1800, there was a new asteroid that was discovered. It's called Ceres. And over roughly 50 days, it was observed by an Italian. And both Legendre and Gauss came up with a way of trying to fit the orbits of comets is something Newton had already done, asteroids and so on. Newton had already done earlier. And what I wanted, so here's Gauss's version of this, Legendre, they both essentially did the same thing. And what I wanted to say is that the method of least squares allows us to represent, once again, I'm using this word representation with seriousness, to represent our data. In this case, I represented the data by the line y equals ax plus b. And in a way, what I did is I was able to find the best value of A and B given the data. The histograms tell you for each representation of the data, I got a slightly different A and B, but you can see that we can represent the data by some sort of regression. That's very interesting. So there's a myriad of other examples of this idea of representation that I could have given you. Spherical harmonics to represent functions on spheres, I've already mentioned that. Lab frame versus moving frame. That's super clever. And really, that strikes right to the heart of the history of astronomy. We had the Ptolemaic worldview, the Copernican worldview. We know that in some sense the Copernican worldview is right. But if I wanted to, actually, in reality, this is the truth. It's most of the time we're on an earthbound coordinate system, and so we have to do hard work to put ourselves in the coordinate system of the sun. Multiple expansions of the potential due to a particular distribution of charge. If I have some weird charge distribution, it's super cool that I can represent that as a dipole plus a quadrupole and so on, octopole or whatever. That's very interesting because it gives us a new way of thinking about the same object. So remember, like I said, same object, new encoding. So I replace this messy, weird shape with a charge distribution with a new encoding, and that encoding invokes words that we understand like dipole or quadrupole and so on. Continued fractions as representations of numbers. And then finally, using summary statistics, I represent a probability distribution by telling you its mean and its variance. And this is going to be central to this next few vignettes, because when we talk about the covariance matrix, in order to construct principal components, for example, we are representing the entirety of a statistical mess that's captured in a histogram or a probability distribution using a summary statistic. So it's a representation of some other deeper object. And then my last way of characterizing this is it is a slightly political comment, and I always pride myself, I suppose, on being not particularly oriented towards politics and the righteousness of it all. But I do find it strange how willing people are to represent themselves by a scalar order parameter. So I won't say who, but I knew somebody very well that said to me, we couldn't vote for person X because we are party Y. End of story. So, what that meant to me was, regardless of anything like the complexity of ethics or the complexity of problem-solving mentality or the complexity of anything, a single scalar order parameter, just a single word. So I can describe, American politics for many people it's a single spin. You're Republican or Democrat. This Enneagram test is a representation of people by another scalar order parameter, which I think is probably oddly, I'm kind of find it weird that I'm saying this, but I think it's a better order parameter than some political nonsense. There's a four-dimensional vector that you could represent called the Briggs-Meyer, which is sometimes given in employment tests. If somebody writes a biography of someone else, that's a representation of that person, but this time a little bit more nuanced with 10 to the 6th letters, but it also can be nuanced in a misleading way because maybe it's got an axe to grind and it's a falsehood. An autobiography might be another 10 to the 6th letter representation, but it could also be misleading for its own reasons because somebody fails to look in the mirror and understand themselves, which is probably more often than not. I think that's true in my case. I'm not sure I really understand who I am fundamentally. So where we are in this whole proceedings then is I've tried to give you a schematic illustration of this notion of representation. And I think that it's super powerful it's something which we need to think deeply about in this age of AI, because representations are afoot everywhere we look. So in the coming vignette, we'll turn to the question of unusual notions of vector.